Hello and welcome to our webinar on black swans and Bayesian networks. My name is Stefan Conradi and I will be your host today. It's great to have you join us and happy Friday, everyone. The term black swan has really become popular when Nassim Nicholas Taleb used it in his book Fooled by Randomness. He followed up a few years later with a book actually titled The Black Swan. And what he pointed out in his book was the following. What we call here a black swan event has the following three attributes. First, it is an outlier as it lies outside the realm of regular expectations because nothing in the past can convincingly point to its possibility. Second, it carries an extreme impact. And third, in spite of its outlier status, human nature makes us concoct explanations for its occurrence after the fact, making it explainable and predictable. Now, you may think Taleb coined that term, black swan. Actually, it goes back a lot further. It first appeared in a satirical poem by Roman poet Juvenal in the 2nd century AD. For those so inclined, I have the Latin original on this slide. So why did he even reference a black swan? Well, until the 17th century, it was believed that black swans actually do not exist. So it was a metaphor for something that is utterly impossible. Now, in modern times, you sometimes hear references to hypothetical extreme events as black swan events, such as an aircraft crashing into a nuclear power plant. That would really be a prototypical black swan event. Fortunately, this particular disaster has not happened, but in many industries, designs have to account for such possibilities. So let me now talk about today's agenda. And it's really about a general research question and then a specific research questions. In general, we want to manage risks related to never seen before events. And more specifically, we want to represent common and rare events jointly. So not just the rare event, but both common and rare occasions jointly in a single model. Now, our case study topic gives us the specific research question. It is about how to find the optimal composition of a pure play portfolio of maritime stocks, considering both common and extreme events. So here's the workflow that we're going to pursue today. First, we will start collecting historical data from maritime shipping companies. We will use BayesiaLab to machine learn a Bayesian network to approximate the joint probability distribution of the underlying historical data. In that context, I will also point out several technical steps that you need to use in BayesiaLab to perform all this. And the next step in this context is that we will want to select stocks. Instead of just selecting all maritime stocks, we want to find a subset of stocks and then optimize that portfolio of stocks given their historical volatility. Okay, so far that was just about capturing normal events. Now comes the time when we will need to hypothesize about other potential risks and elicit assessments about them. Things that have never happened before, but that could happen and may impact our stock portfolio. So then we will need to augment our machine learning network with such judgments, with such hypothetical conditions, etc. So that's what we need to bring together in a Bayesian network. And then once we have that, once we have the common historical relationships and the potential extreme events encoded in the same Bayesian network, then we can optimize our portfolio and given both common and hypothetical extreme events. All of this we will be doing with BayesiaLab. That's our platform for encoding, learning, editing, analyzing, simulating, optimizing Bayesian networks. And of course, BayesiaLab is just one small component. Well, it's the major component, it's our core product, but it really belongs into an ecosystem of desktop software, web applications, and APIs that all kind of build on each other. And for instance, in today's context, the Bayesian expert knowledge elicitation environment would be quite useful because we could utilize that to elicit expert opinions about such rare events. We don't have time for that, so we will just focus on the encoding and the optimization part today. So everything you see today, all slides, all networks, plus a video recording of this webinar will be available. It will be posted either later today or sometime over the weekend. Now, in terms of questions, we have way too many participants to handle all questions online. So I'd ask you to post your questions via the chat panel that you can bring up in your Zoom window. So, and then we will answer your questions on offline. All right. Before we start talking about extreme events, let's talk about normal risk, often referred to as volatility. And we can nicely illustrate this with the stock market. We have an abundance of data from which we can establish many statistical measures. You can read about trends, betas, variance, returns, and investment advisors make a living managing portfolios based on such statistical measures. And one of the key principles in this context is the concept of trading off risk and return. It has been formalized by Harry Markowitz in his 1952 paper named Portfolio Selection. And what he writes in this paper is, or really the key sentence to me is this: there is a rate in which the investor can gain expected return by taking on variance or reduce variance by giving up expected return. Okay, here's the next slide. So this work by Markowitz gave rise to modern portfolio theory. He has formalized this and really says for any given level of risk, there is an optimal portfolio that can maximize the expected return. So as you compose your stock portfolio, you want to be on that so-called efficient frontier that maximizes the return for any given level of risks. You may have seen this plot before in the literature, in the financial literature. It is a very, very familiar concept. So all this works beautifully until it doesn't. Needless to say, statistical measures and models can only capture what is contained in historical data. And I'm stating the obvious when saying that future catastrophes don't appear in any data. And I'm not claiming that we can predict what will happen. However, I think we can speculate about what could happen. We can think of catastrophic scenarios and hypothesize about them. However, that requires that we build models that go beyond data. In addition to statistical relationships from historical data, we need to introduce theoretical considerations. We need to think about what could happen and what the dynamics may be. So our model will no longer just be sourced from data, but also from theory. And as you can imagine, that's where Bayesian networks come into the picture. They are the framework that allows us to capture knowledge from data and capture domain knowledge as well, expert knowledge. And we're going to illustrate how we can merge the two in the context of defining an investment portfolio. We want to be able to understand risk, quantify that risk, and finally we want to optimize our portfolio with this model that with this Bayesian network model that contains both expert-derived knowledge and data-derived knowledge. So let's illustrate this in the context of a very simple case study, I should say a simplistic case study. We want to develop a pure play portfolio of maritime shipping stocks. Why do we want to take the seas? Well, perhaps we're contemplating the expected growth in global trade and the corresponding need for shipping capacity. So here, for instance, you have the forecast as to how global trade will grow. China, India, for instance, in the high single digits, that is quite significant. That is forecast annually for all the years on average through 2030. So that's our motivation for our case study. And there are two sectors in particular that are of interest here, as defined by the NASDAQ categories, and that is water transportation and deep sea foreign transportation of freight. And here are all the companies that are listed on American stock exchanges that fall into these categories. So, but even if we just consider those companies listed in the US, there are dozens in the maritime sector, and we now have a very large number of assets to choose from to build our investment portfolio. So let's now start building that, composing that portfolio, but initially just with or under normal conditions. Let's say we have a smooth sailing ahead. Let's look at our historical data. We start off with a large flat file containing the stock returns of all the companies we just saw, whose names we just saw on the slide. More specifically, we've taken the returns of 10-minute intervals in regular trading sessions from the beginning of this year, 2019, through last week. One can now argue whether this is the appropriate time frame to observe or to study, but that's not really the point of this presentation. We want to illustrate the conceptual workflow, and this seemed like a convenient data set for a proper approach for formal portfolio optimization. You may very well choose a longer time frame or a shorter time frame, or just look at daily returns or weekly returns. That's entirely up to the analyst. We had this data set available, and we thought this will be very practical for our purposes. So let's switch into BayesiaLab and bring this data in. We start with the data import wizard. You see a screenshot of that here. It shows us in all the columns the stocks with their ticker symbols, and in the first column we have the date time stamped. Very straightforward. Chances are you have seen this before. Here in this case, we want to define the date timestamp as a row identifier that uniquely identifies each time frame, each row in our big table. Missing values processing is important here as well. Not all of these stocks were continuously traded. There were basically breaks in some of the time series, so we need to deal with missing values. Now, we've covered that particular topic in other papers and webinars, so I'm not going to elaborate on this any further. Next step is discretization. Here we have a fairly large data set, lots, like 4,500 observations or so, which make the discretization fairly straightforward and not a big topic that is of importance here. If we had a lot fewer observations, it would be much more of an issue. Here, I will use kind of a default discretization algorithm, the R-squared genopt, with 5 intervals. Now, later on, we can discuss what is the appropriate number of intervals for discretization, but let's start with this. So we click the Finish button and now see a graph panel with the initially unconnected Bayesian network. So here we have all the stocks that we have imported with their ticker symbols, and little question marks indicate that some of these have missing values. So now these are not very big brand names, so I suspect that you may not recognize many of these ticker symbols. For that purpose, we're going to associate a dictionary with long names. That's very helpful, that we can switch between short symbols and long names, more explicit names, because short ticker symbols are nice to have on the screen. They keep the presentation nice and compact, but then if we want to know, well, what's the company behind it, we can quickly switch into long company names. So I'm basically loading a text file that links up the ticker symbol and the long company name. Then I turn that on, and so now you see the view with the long company name. So we can see, well, here are some better known companies, Carnival Company, what else is perhaps better known? Well, some of the others are, yeah, I at least wasn't familiar with until I started on this case study. Anyway, given that these are not familiar brand names, I will do one more step. I will assign classes. I simply looked up, well, what do they ship? I mean, with Carnival Cruise Lines, it's obvious they ship people on holiday cruises. Others, we have to see what they do. And here I simply created a dictionary that says whether a company is in oil transportation, gas transportation, dry bulk, or container shipping. So I've defined those classes again in a text file table and bring that in. And then what's a very nice feature of BayesiaLab, we can color code them. We can associate each of the classes we defined with a color. So for instance, petroleum tankers are black, black as oil, gas carriers are white, dry bulkers are gray, cruise ships are green, and so on. So we can now, each of the nodes has the appropriate color. So, however, we don't want to use all of them because we said we're interested in maritime shipping. So in this context, perhaps cruise lines don't fit in, and also offshore services, companies that service oil platforms or barges and so such things, we don't want to include. So I'm selecting those classes and exclude them, and then update our layout. Here I'm going to use a staggered layout, so I have a nice compact presentation. Okay, now we're ready to do our first learning. We now want to get a sense of how all these companies, or rather their stock price returns, relate to each other over time. A good starting point for learning is unsupervised learning, more specifically the maximum weight spanning tree, because it is so quick and easy. So it gives us a quick sense of, well, what's related to what. That's the output. Now this is a screenshot, but had we done it in real time, it would have been just as quick. So maximum weight spanning tree is a very, very quick learning algorithm. Okay. So in this particular view, it's difficult to really interpret in any meaningful way. So I use the automatic layout to stretch this out, to spread out this network. And now we can see a structure emerging. Given that we have a relatively short period that we observed, just about 6 months, it seems like that some of the stocks aren't connected. They're not related. Perhaps there's just not enough information, not enough history to clearly establish these relationships. And we're good with that. We will focus on the stocks that are currently in this network. Now, of course, we could spend a considerable amount of time now using different learning algorithms and see whether there perhaps another learning algorithm, a different structural coefficient, would lead to a network that includes other nodes. But here, for our purposes, while these are all would be prudent steps to do, for our purposes, we will just stick with this and utilize this for our subsequent analysis. There are obviously so many detail areas where we could dig deeper and explore different aspects of BayesiaLab, validation, etc. But then this would become a 6-hour webinar instead of a 60-minute webinar. So what we want to do with this particular network now is see what clusters there may be. Whether variables group together. It's kind of a silly question because we can already see by the colors that appear that kind of the gas carriers, the container ships, the oil tankers, and the dry bulkers cluster together in this network, kind of the way it is structured. So, but here we can do that very formally with BayesiaLab, extract these clusters formally, not based on our domain knowledge, but rather based on the relationships that exist in this data set. So a very clever way of doing it, or a very good way of doing it, is using the mapping tool. Here we can at the same time also see the importance of the nodes. We can, for instance, highlight the node force that tells us, what are the big players. Okay, in this context, in the context of clustering and mapping those clusters, BayesiaLab allows us to select the number of clusters we want to define. And here we can experiment with and use the slider in the upper left-hand corner to look at 1, 2, 3, 4, 5, 6, 7, any number of clusters. And here what I think it would be appropriate, and this is very much a judgment, if we select 4 clusters through the variable clustering algorithm, it interestingly coincides with petroleum tankers, gas carriers, container ships, and dry bulkers. Perhaps this is not at all surprising, but it is nice to see that the data in a way confirms our domain knowledge. So plausibility checks, sanity checks are always a very good element in such analysis. So now, if you look closely, you will see that the nodes representing the clusters have a name on them, and that represents the manifest variable, the strongest underlying variable within each cluster. So for petroleum tankers, it's Euronav. For container ships, it's C-span. For dry bulkers, it's Genco. So those are the stocks that are most defining, most informative with regard to that cluster. And if you've seen some of our webinars on clustering and probabilistic structural equation modeling, you may already be familiar with some of these concepts. In any case, we don't want to take the clustering any further. We don't want to formally introduce clusters. Rather, our objective is to find individual stocks. What I'd like to do is simply pick the stocks that are most representative of each of these clusters. And in this case, I'm simply taking the ones that are shown here: Euronav, C-span, Genco, and Gaslog. So I'm simply selecting this subset of nodes and say, they are kind of representative of each of these subsectors of each of these clusters. So let me use those in my investment portfolio. Certainly, I would also do some fundamental analysis, look at all other published company measures. But for now, let's assume that that's all okay. So I'll take these 4 companies, exclude all the other ones, and attempt to build our portfolio on this basis. So now zooming in a bit. So we now have a company for petroleum tankers, dry bulkers, container ships, and gas carriers. And now, of course, the question is, how should we allocate our portfolio here? What should we, should I invest 50% in Euronav and whatever? That is the question now. So how would we go about that? Well, we start off by performing unsupervised learning now just on this subset of variables. And now we need to think about how we can trade off risk and return given the historical data. That's our task now. We want to figure out, obviously we want to minimize risk and maximize return, but according to theory, there is a frontier. And of course, we want to get as close as possible with regard to that frontier. And really, so we get the maximum expected return for a given risk. Now, there are a number of optimization algorithms that would allow you to compute the point on that efficient frontier given your stock portfolio and your risk appetite. And here, this is how we would traditionally, in the context of modern portfolio theory, compute these. The expected return is simply the sum of the individual stock returns. The W denotes the weight of the stock, the weight, basically the percentage of the portfolio. Similarly, we would compute the variance as shown on this slide here. This just refers, for instance, to a 2-stock portfolio. Now, this seems straightforward, but there has been a lot of criticism about this approach. One of them being that the assumptions of normal distributions in modern portfolio theory may not hold. That may not be realistic. And perhaps we'll see this later on when we look at the distributions of our stocks. A further criticism is that looking at variance or standard deviation as a measure for risk or volatility is not appropriate, because really we would see downside as a risk, but upside really as an opportunity. So if there was volatility that just goes to the positive side, we would perhaps be fine with that. And then finally, and this is really the crucial point for today's webinar, modern portfolio theory provides a statistical, not a structural model. So we're just looking back in time and measuring relationships from that, but we're not taking into account what could potentially happen. So what are we going to do with that? Well, regarding the first point of criticism, what we're going to do is we're going to learn a Bayesian network. So we will no longer make any assumptions about linearity or distributions. Bayesian networks will help us overcome that. For the second one, for the fact that variance is a symmetric measure, but risk is not, we could define a new risk score. That would be very easy. And we could just make up what we like, but we're not going to do that because that's not really all that important for the point of today's webinar. And then finally, this is really the interesting part. Modern portfolio theory provides a statistical, because modern portfolio theory provides a statistical, not a structural model. In a Bayesian network, we can encode assumptions. That's That's very, very important. So that's what we will do. So let's start here and let's now learn a Bayesian network. We will, as we did earlier, we start with unsupervised learning. We will learn a model based on these 4 stocks, and these 4 stocks are now being approximated, or now approximate the joint probability distribution of the historical data. We can analyze that. We can just examine the relationships. Interestingly, when we look at them, they are indeed not linear. We just do a target mean analysis, which is one of our visual analysis tools, and it will quickly emerge, yes, they are not linear. So one of the assumptions of the modern portfolio theory no longer holds. So, but now that we have the network, now that we have the joint probability distribution captured, we want to use this to mix our stocks into an optimal portfolio. We want to maximize the expected return given a certain level of risk. So for that, we now take this network and plug it into what I call an optimization framework. This looks like a fairly convoluted structure, perhaps, but let me take you through what this structure does, what this Bayesian network will do for us. So let's perhaps start here with the top row. So these are the asset weights. These are new nodes that by default I have set to a 25% value. They represent the default weight. This would be if we just had an equal share of all stocks in our portfolio. That's what we will start with. And those are also the variables that we will modify. Now, the next set of nodes are function nodes. They will take the distributions of the asset weights and translate that into a single numerical value. This is just for convenience, which makes the working with this type of Bayesian network easier. So that will just give a single numerical value. So in this case, the distribution that has a mean value of 0.25 is now a numerical value of 0.25. Here is our network. That network captures the joint probability distribution that we've learned earlier. We have simply plugged that into this bigger computation framework. Then the next set of variables, they actually don't do a lot. We just need those to sum up the values. So as our weights modify the distributions and mix them, these nodes, the summation nodes, just add up everything. All goes down into a single node, here named PR3. That's now the final distribution, which is the sum of the distributions in the network subject to these weights. Okay, and then at the very bottom, that's where we have our scoring function. We compute the expected return, essentially taking the mean value of the node PR3, and we also use the function node to compute the standard deviation. That's our proxy for our measure of or capturing variance. And then at the very bottom, I have a node that is called portfolio score, and I'm using this to or it's kind of an arbitrary function where I'm basically weighting expected return and standard deviation. And this is really something you can use as you wish or define, or also depending on how you value upside versus downside and how you want to balance that. So, all right, now we have that. Now we have the structure. We have our our Bayesian network as the calculation framework overall, and then in particular the network that captures the joint distribution from our stocks. All right, now we're ready to optimize. Now what we want to do, we want to modify the weights such that we can maximize our portfolio score at the very bottom. Now, there are a few things we need to consider, and that is, for instance, we need to set a constraint that all the weights should add up to 1. We want to allocate 100% of our capital, and so we can't have the sum of our weights exceeding 1. So that's what we define. And then additionally, we're defining a target value, or in this case, I just randomly selected 1 as a very high value so that BayesiaLab and this genetic optimization algorithm maximizes that. Furthermore, I'm telling BayesiaLab, save the best solutions, and I'm setting a stop criterion that basically gives me a result after, in this case, 10 attempts. If the score doesn't improve after 10 iterations, then BayesiaLab stops and gives me the result. Now this can take a few minutes perhaps. Here I'm simply fast forwarding to the result, the way it would appear with the optimization report. Here in the synthesis table, you can see the best solution. You can also see the initial state highlighted in yellow. So it basically tells us we should reduce the share of URNAV, reduce the share of GASLOG, increase GENCO, and decrease C-SPAN. So that would be the best solution. The single best solution, but also all the other best solutions, the second best, third best, and so on, are saved in the scenarios. That's this little box in the lower right-hand corner. That's where we can recall the scenarios, and I'll show that to you momentarily. Just one comment on the console at the bottom. There you can see, while the optimization is running, the progress of the solution. So there you can monitor the score and can see whether this is going in the right direction or whether it is improving any further. Now, I had mentioned the scenarios. By right-clicking on the bottom right icon, this orange box, there I can retrieve these scenarios and really look at them and simulate them and perhaps experiment with them a little bit further. So, but you may now say, okay, this is not very interesting because we've been doing this all along with portfolio optimization. We just have now a slightly better mousetrap, not perhaps even, perhaps not even much better. So let's assume now that we went ahead and invested in this proposed stock portfolio, and we're perhaps confident that we did the right thing. But now let's hypothesize as to what might happen, what could potentially happen as a worst case scenario in the world of shipping. So here's something perhaps to consider. For instance, let's look at one of the world's busiest shipping routes that goes from the Persian Gulf via the Arabian Sea, Bay of Bengal, Strait of Malacca into the South China Sea. So this, or in particular the Malacca Strait, is the busiest strait in the world. Over 100,000 vessels pass through each year. And in fact, almost half of the world's trade tonnage passed through that point. For instance, also, China receives 75% of its oil imports through this point. The problem is that the Malacca Strait is a choke point. It is at its narrowest point just 1.7 miles wide, and plus it is very shallow, typically less than 100 feet deep. So one can imagine that incidents of many kinds could further constrict this choke point. So, and now let's think about what could this be, what could happen. And it would be very easy to imagine that there could be political tensions between major players in the region like Malaysia, Indonesia, China, and that some political military conflict might emerge that will lead to a Navy blockade of the Malacca Strait. So here's your black swan event. Or there could be a nuclear submarine disaster in the Malacca Strait that would obstruct civilian traffic, naval traffic, and thus block that very important shipping route. So if this were no longer available, then what? Well, there are alternative routes like the Sunda Strait, Lombok Strait, but you can see that this would obviously be a major detour, add many days to a vessel's voyage, and therefore cost more. So obviously, as investors, we can't do anything about that. We can't fix the problem, presumably. However, we can perhaps account for such problems, such potential problems, in our investment decisions. So we need to think about, well, what could happen in the stock market regarding our portfolio under such conditions. So, of course, such incidents are not in our Bayesian network because it has never happened before. So the question is, how can we account for such risks? Well, we need to theorize about them. We need to think about what could happen and what would that do to our stock portfolio. And that really brings us to the third point of criticism about modern portfolio theory, that it just captures historical data and is not a structural model. Now, I don't want to pretend that we can build a full structural model as to how all these things, how military conflict would cause our changes to our stock portfolio, but we can make statistical assumptions. Well, how probable or how improbable is that? How would that affect our portfolio? So this is what we're going to do. We now will augment our original network that represents the joint probability distribution in such a way that it reflects our estimates of an extreme event. So for instance, we can speculate that perhaps oil tankers and gas carriers in particular are affected because that is really the route they take between the Gulf, the Persian Gulf and the South China Sea, going into China, supplying oil to China. So perhaps those are particularly affected. And so I'm creating this node that captures an extreme downturn, an extreme negative return for those stocks. Now, historically, that has happened very, very rarely that both of these stocks declined simultaneously. But I'm hypothesizing if the Malacca Strait is blocked, both of these stocks would be impacted. They would be affected, and we would observe a serious downturn for both of them simultaneously. So I'm adding this node, this extreme event node, to my existing Bayesian network, and therefore change its joint probability distribution. I'm augmenting this network and therefore changing it. So here I'm just doing this again, what I had zoomed in the previous slide. And this is very important, historically, those downturns were very, very rare between those two stocks simultaneously. But now I'm saying I'm assessing this anew. I'm perhaps observing the political developments in this region, and I'm changing this potential occurrence of this extreme event, and I'm saying this is tenfold more probable. So historically, we've seen the downturn only on 0.05% of all observations, and now increasing that to 0.5. So I'm doing this, increasing this significantly, because I'm saying over the period that I'm anticipating, that's the probability. Now, this number is obviously entirely made up. I'm just using a number to illustrate the concept. So now that we've set this, we can run a new optimization. We've changed the joint distribution. We've added our anticipation of an extreme event to our historically generated joint distribution. So we're running the optimization again, as we did before. We're setting the same constraints here in the sense of target resources. They need to add up to 100%, and then run this again. And sure enough, given what we have set in terms of a probability of an extreme event, now we get a different optimal solution. So now maximizing our score is a different mix of our 4 stocks. We can look at this again. We can recall that via the evidence scenarios. We can look that up. And here it seems like it's actually a significantly different mix. We now have Euronav and not Euronav. We have that would be Genco and Gaslog Partners as the biggest stocks, and Euronav and now I forgot the name of the company with the ticker symbol SSW, that would have the smallest share in this portfolio. Now again, totally fictional numbers, so it's not worth really debating this any further, whether this is plausible or not. I wanted to illustrate this conceptual approach of taking historical data, learning the joint probability distribution, and then augmenting it, thus arriving at a new optimal solution. Of course, now you can make this work with a much larger set of stocks. You can add many more events of different kinds. You can set multiple extreme events affecting different companies, different stocks, and then perhaps even define the co-occurrence of different types of extreme events. Natural disaster, war. You could speculate what happens if you have a military conflict around the Malacca Strait, plus you have a tsunami happen at the same time. Then what? Of course, very improbable, but would have major consequences if it were to happen. So this is an approach how to deal with it. All right, in conclusion, I would like to point out that we do many seminars and courses beyond webinars like today. For instance, we hosted a course in Washington, D.C., our new BayesiaLab 101 course earlier this week. At the very moment, we're conducting a 3-day course in New York City, and we have programs like that throughout the year. The next ones that are coming up is our introductory and advanced course in Paris. I need to point out that even though this course is in France, it will be conducted in English. And then in the context of our annual conference in Durham, North Carolina, in October, we'll also have an introductory and an advanced course. In addition, we're planning further webinars and further instances of our BayesiaLab 101 course for the rest of the year. I had already mentioned the BayesiaLab conference. Even if you're not interested in a course, our annual conference is a great way to learn about all the possible applications of Bayesian networks. It's really a broad spectrum of use cases. We will have presenters from medical research, finance, military. It will be really a broad range of applications that will be presented there at our conference. It's a great event. It's a fun event. A great community of researchers, scientists, and practitioners that are coming together. Now, perhaps if you're new to Bayesian networks, you would like to try out what I showed today. We have a simple demo version that you can instantly download from our website, or you can also apply for an unrestricted 30-day evaluation version that gives you all the features for doing what we did today. So you may want to try that. We have a community forum, great place to discuss topics related to Bayesian networks, share best tips and tricks. A great way also to get engaged in this community. So with that, I would like to thank you for your interest, for your attention. I would love to stay in touch. Please feel free to reach out with questions. You can email me directly. Please connect with us on Facebook or LinkedIn or follow us on Twitter. As I said, I would love to continue the conversation with you, or perhaps see you again at one of our forthcoming events or seminars. So with that, thanks again and have a fantastic weekend.